Hypothesis testing. Here are the sections in this reading. Let's say you have a population which consists of returns on all Asian stocks last month. Assume for a moment that there are about 10,000 publicly listed stocks in Asia. So that means that you have 10,000 numbers. You are a researcher and believe that the average return on all Asian stocks was greater than 2%. So you have a view about the population mean denoted by mu, and your view is, or your assessment is, that the mean return was greater than 2%. When we talk about hypothesis testing, what we do here is express our opinion or assertion as a definitive statement. That statement is called the hypothesis, and we are going to learn how to define a hypothesis. After defining the hypothesis, we draw a sample from the population, and then we study the sample to evaluate whether our assertion makes sense or not. Or to put it in more formal language, we assess whether our assertion is statistically significant or not. Here are the 7 formal steps that we follow in hypothesis testing. What you need to do is pause the video over here and try to memorize these 7 steps. From an exam perspective, it makes sense to understand these 4 critical steps. To do hypothesis testing, we first state the hypothesis. We then compute something called the test statistic. Next, we determine a critical value which is based on the significance level. And finally, we compare the test statistic with the critical value and determine whether or not to reject the null hypothesis. Over the next few minutes, we will go over each of these items in detail, because the most likely scenario on your exam is that you will be tested on one or more of these steps. Let's start with the first step, which is stating the hypothesis. And we go back to the original assertion or original comment that we made on the introductory slide. You are a researcher and believe that the average return on all Asian stocks was greater than 2%. Here is how we express this in formal terms as a hypothesis. There is something called a null hypothesis, written as H0, and this is the hypothesis that we typically want to reject. Mu stands for the population mean, and mu naught stands for the hypothesized value. In our simple example, the null hypothesis is mu naught is less than or equal to 2. Given that you believe that the returns are greater than 2%, you want to reject the hypothesis that the mean return is less than or equal to 2%. The alternate is what you are after, and this will be mu greater than 2, because that is what your view is. Just to hammer in the point and make sure you understand and remember what we are talking about, the null hypothesis, H0, is usually the hypothesis that the researcher wants to reject. H0 always includes some form of the equal to sign, and that you see right here. We could have had the equal to sign as part of the null or as part of the alternate. The convention that we follow with hypothesis testing is that the equal to sign is always part of the null hypothesis. It is a rule, just remember it. The alternate hypothesis is accepted when the null hypothesis is rejected. It is usually the alternate hypothesis which we are trying to assess. Item 2. Compute the test statistic. A test statistic is a quantity calculated based on a sample whose value is the basis for deciding whether or not to reject the null hypothesis. This is the formula for calculating the test statistic, where you are interested in the mean of the population. So going back to our earlier scenario, our population consists of the returns on all Asian stocks last month. Let's say that we know the population variance and standard deviation. Our hypothesis is related to the population mean. We draw a sample and our sample size is 36. The sample mean is 4. So the 36 stocks that we come up with over here, we take the mean return for those 36 stocks and our number is 4%. The way we calculate the test statistic then is, say, sample statistic, which is 4, minus the value of the parameter under H0. Now let us just recall what that means. We write down our null hypothesis again. Remember, the null hypothesis was that mu is less than equal to 2 and the alternate was that mu is greater than 2. This number is the hypothesized value or the value of the parameter under the null hypothesis. So 4 minus 2 divided by standard error of the sample statistic. We saw this in the earlier reading on sampling. The standard error is given by sigma over root n. In our case, sigma is 4, root of n is root of 36, which is 6. So if we do the maths, what we get is 3. So the test statistic based on these numbers is 3. Then we have to come up with the critical value based on a significance level. And we've seen this in the earlier reading also. Say you want to perform the test at a 5% significance level. And 5% significance level is the same as 95% confidence. Remember this normal distribution. 95% confidence or an area of 0.95 over here meant a significance of 0.5, which means an area of 0.05. The critical value is the z value, which corresponds to this area in the tail. If you look at your standard normal distribution or the z distribution, the number over here, which corresponds to a probability of 0.5 on the right and 0.95 on the left, the number is 1.65. This is the critical value. So we have answered the critical value, which is 1.65. Is this a one-tailed test? The answer is yes, because we are only looking at one tail over here. We will see tests later that involve looking at both tails. Those tests are called two-tailed tests. Next, we compare the test statistic with critical value and make a decision. If the test statistic is greater than the critical value, then we reject the null hypothesis. If the test statistic is less than the critical value, then we fail to reject the null hypothesis. If we look at our situation, the test statistic was equal to 3 and the critical value was 1.65. Since the test statistic is greater than the critical value for our situation, we reject the null hypothesis. The way we can express this using the probability distribution, we have a critical value of 1.65 over here. If the test statistic falls to the right of the critical value, that is the region where we reject the null hypothesis. If the test statistic falls to the left of the critical value, then we fail to reject the null hypothesis. Here again, I have shown you the null hypothesis and the alternate hypothesis. Now, in case you are wondering, how did we know that we need to deal with the right tail as opposed to the left tail? The first remark here is, whenever you have a less than equal to sign in the null hypothesis or a greater than equal to sign in the null hypothesis, as opposed to a plain equal to sign, which we will see later, that means that we are only dealing with one tail. And just as a hint, take it as a given for now that if you have a greater than sign, so that is pointing to the right in the alternate hypothesis, that means that we will deal with the right tail. The alternate hypothesis sign points to the rejection region. In case you are wondering why, I'll give you a brief explanation now, and as you spend more time with hypothesis testing, this will make more sense. Now, think about the formula for the test statistic. The formula was x bar minus mu naught, which is the hypothesized value, divided by the standard error. Let us just focus on the sample statistic relative to the hypothesized value. If the hypothesized value is 2, and your x bar is a very big number relative to 2, then that is going to increase the value of the test statistic. A higher value of the test statistic means that your assertion is probably correct. And notice that a higher value of the test statistic would mean that you are somewhere on the right. The question now is, how much on the right must you be in order to reject the null? That point is given by the critical value, which is based on the significance. So this critical value of 1.65 is not based on x bar or mu naught. This is coming from the fact that you are using a significance level of 0.05. Now, you can reject the null hypothesis if this number is larger than 1.65, and the larger number comes either because of x bar being large or the standard error being small. Now, whether or not you understood this, just remember that if you are using a greater than sign in the alternate hypothesis, then you always deal with the right tail. Let us look at a situation where you are playing or dealing with the left tail. So take another situation now where you believe that the average return on all Asian stocks was less than 2%. The hypothesis then becomes the following. Null hypothesis is what you want to reject, and the null hypothesis must have the equal to sign. So you will have mu greater than equal to 2. The hypothesized value is still 2. And the alternate hypothesis is that mu is less than 2. The test statistic, given that sigma is 4, n is 36, and x bar is minus 3. Remember the formula because it is extremely important. The formula is x bar minus mu naught divided by the standard error. So that is equal to x bar is minus 3 minus mu naught, which is 2, divided by standard error, which is 4 over root 36. And when you do the maths, you should get minus 7.5. The critical value with alpha equal to 0.05. Now, if you draw your distribution, now remember which tail will you play with? The alternate hypothesis has the less than sign. That means you have to play with the left tail. The critical value now is minus 1.65, because if this region is 0.05, or that's the area or the probability, then the corresponding value or z value is minus 1.65. That is the critical value or the rejection point. Notice that our test statistic now is falling way to the left. So test statistic is falling somewhere over here at minus 7.5. With a left tail test, if our test statistic falls to the left of the critical value, then we reject the null hypothesis. So in this particular scenario, to the left of minus 1.65 is where you reject the null hypothesis, and to the right is where you fail to reject your null hypothesis. Let us now look at a two-tailed test. And the situation here is slightly different, where you believe that the average return on all Asian stocks was not 0%. So what is the hypothesis? The null hypothesis is what you want to reject, and it must have some form of the equal to sign. So the null hypothesis is that the population mean is equal to 0 versus the alternate that the population mean is not equal to 0. In terms of the test statistic, we are given this data where sigma is 4 as before, n is 36, but x bar, the test statistic, is equal to 1. The formula is the same. It's x bar minus mu naught divided by standard error. In this particular case, mu naught is 0. So we have x bar, which is 1, minus 0 divided by the standard error, which is still 4 divided by square root of 36. So our answer is 1.5. That is our test statistic. For the critical value, we look at the normal distribution here, and notice that our alpha is still 0.05. I had not mentioned that earlier, but let's say that we want to use the same alpha that we have used before. Now, alpha 0.05 is now distributed across both tails, and the reason is our null hypothesis is that mu is equal to 0. That means that if there is a deviation on either side, in other words, if your sample mean is very high, then you can reject the null, or if your sample mean is very low, then you can reject the null. The sample mean is what is driving the value of the test statistic. So we need two critical values now, or two rejection points. With alpha equal to 0.05, in the right tail, we need to have half of 0.05, which is 0.025. In the left tail, we also have 0.025, and in the middle, we still have 95% or 0.95. So if you look at your z tables, you will notice that with 0.025 in the right tail, the critical value is 1.96. With 0.025 in the left tail, the critical value is minus 1.96. With a two-tailed test, this region in between is where you fail to reject the null hypothesis, and the region to the right of plus 1.96 is where you reject the null hypothesis, and also the region to the left of minus 1.96 is where you reject the null hypothesis. If we look at our test statistic, it is 1.5. That is somewhere over here, and since this is in the in-between region, that is where we fail to reject the null hypothesis. So our decision is that we cannot reject, or we do not reject, the null hypothesis. Many students get confused between one-tailed and two-tailed tests. So on this slide, I have simply summarized the main points related to one-tailed and two-tailed tests. As we've discussed, with one-tailed tests, you are only concerned with one tail, be it the right or be it the left. When you have a greater than sign in the alternate hypothesis, then you are dealing with the right tail. When you have a less than sign in the alternate, then you will be dealing with the left. Generally, when a researcher wants to test whether the return on a stock is greater than a hypothesized amount or less than a hypothesized amount, that's when you use one-tailed tests. With two-tailed tests, we allow for deviation on both sides of the hypothesized value. And we just saw an example of that, where the researcher wants to test whether the return on stocks is different from a hypothesized value of 0. In that particular case, mu naught would be 0. So whenever you see a plane equal to in the null hypothesis, there has to be a not equal to in the alternate, and this would be a two-tailed test, because here we are dealing with deviations on both sides of the mean. Because here we are dealing with deviations on both sides of the hypothesized value. Now we look at the relation between confidence interval, which we studied in the last reading, and hypothesis test, which we are studying in this reading. We continue with the example that we've been talking about. We have a population which consists of the returns on all Asian stocks last month. The population standard deviation is 4. We draw a sample, and the sample has a size of 36, and the sample has a mean of 1. Let us say that we want to do our work with 95% confidence. which is the same as a significance level of 0.05. If you recall, the confidence interval for this situation is x bar, which is equal to 1, plus or minus z alpha over 2. We call this the reliability factor. Alpha is 0.05, so alpha over 2 is 0.025, and the number that corresponded to 0.025 is 1.96, multiplied by the standard error, which is sigma over root of 36. When we do the maths, essentially we come up with the following, that we can say with 95% confidence that the population mean is between minus 0.3 and plus 2.3. This is a quick recap of what we saw in the last reading. With hypothesis testing, the first thing we need to do is express the hypothesis, which is that the null hypothesis is mu equals 0 versus the alternate that mu is not equal to 0. Here you believe that the population mean is not 0. That's why we have the not equal to sign here in the alternate. We compute the test statistic, which is 1.5, and this test statistic is based on x bar minus mu naught, which is 0, divided by the standard error, which is 4 over 6. So notice we are using similar numbers in both cases. The critical value is plus or minus 1.96, which also was used with the confidence interval. And again, critical value is based on the fact that we have a significance of 0.05, which is split across both the tails. So in each tail we have 0.025, which means that these numbers are plus 1.96 and minus 1.96. And then we notice that the test statistic falls within those critical values, so we do not reject the null hypothesis. Now, if you look at both these conclusions, in a way they are saying the same thing. On the left, the confidence interval is saying that 0 falls within the range. So in a way, the null hypothesis, or in a way this result from hypothesis testing, is also telling us that we cannot reject the fact that the population mean is equal to 0. Now, to put this more formally, if the hypothesized value is inside the confidence interval, which is the case over here, the hypothesized value of 0 is in the confidence interval, then the null hypothesis is not rejected. That is the situation we have given the data that we collected. However, if the hypothesized value is outside the confidence interval, then the null hypothesis is rejected. We now change gears a little bit and talk about the p-value. The p over here stands for probability. This essentially gives us another way to reject or not reject the null hypothesis. I'll start with the formal definition and then explain what p-value is all about. P-value is the smallest level of significance at which the null hypothesis can be rejected. You will understand this statement once we have gone through the discussion on the slide. The most basic way to think about the p-value is that it is closely related to the test statistic. In fact, if you know the test statistic, you can automatically figure out the p-value, and if you know the p-value, you can automatically figure out the test statistic. So there is a one-to-one correspondence between p-value and test statistic. More specifically, a high test statistic means a low p-value. So let's say that you have a test statistic that is equal to 1.65. If the test statistic is 1.65, then the p-value is this probability to the right of 1.65. So that p-value then is 0.05. If your test statistic is 1.96, then the p-value becomes smaller. Then it is this area over here, which is 0.025. So notice as the test statistic increases or moves to the right, the p-value or the probability comes down. And using the tables, you can find the p-value that corresponds to a corresponding t-value, and similarly you can find a t-value corresponding to a particular p-value. So that is what I mean when I say there is a one-to-one relationship. We can use the p-value to determine whether or not to reject the null hypothesis. If the p-value is less than the significance level, so if you have a situation where the significance level is 5%, so that means you have 5% over here, and the p-value is smaller, so let's say the p-value is 0.001, that means that you have this probability or this p-value. If this p-value is less than 5% or less than 0.05, then clearly you reject the null hypothesis. That is analogous to saying that your test statistic is greater than the critical value, because the significance level is essentially your critical value. So that is, there is a one-to-one relationship between the significance level and the critical value, and there is a one-to-one relationship between the p-value and the test statistic. So you can try this out with some numbers on your own and you can practice some questions, but this relationship should become obvious. And if your p-value is greater than the significance level, so if the significance level is 0.05 and your p-value, for example, is 0.06, then you fail to reject the null hypothesis. Next, we talk about type 1 and type 2 errors. When you do hypothesis testing, there are two possible decisions you can make. Either you do not reject the null hypothesis or you reject the null hypothesis. In terms of the true situation, again, there are two possible true situations. Either the null hypothesis is true or the null hypothesis is false. Let us now look at the four possible scenarios. Scenario 1 is that your decision is do not reject the null hypothesis, while in reality the null hypothesis is true. So this would be a correct decision. The other possibility is that you reject the null hypothesis, which means that you essentially accept the alternate, but in reality the null hypothesis is true. So this is clearly an error, and this type of error is called a type 1 error. You simply need to remember this fact. The next fact you need to remember is that the probability of a type 1 error is the significance level, which we have talked about earlier. So just to express that formally, the significance level, generally denoted by alpha, is the probability of a type 1 error. If you decide not to reject the null hypothesis, but the null hypothesis is actually false, then that is also an error, and that is called a type 2 error. If you reject the null hypothesis and H0 is actually false, then that is a correct decision. The probability of this happening is called the power of a test, and the power of a test is 1 minus the probability of the type 2 error. When more than one test statistic is available to conduct hypothesis testing, select the most powerful. Most powerful means that this probability, power of a test, is the highest. This item is fairly testable, and notice that you have learned several buzzwords over here which you need to be on top of. Let us say you conduct a test and your result is statistically significant. Does this mean that you should automatically go make an investment decision or economic decision without any further analysis? That is what this slide is all about. The material here is fairly self-explanatory, and I will just highlight the bottom line, which is to say that statistical analysis is simply one of many tools which help you make an investment decision. You need to consider several other factors such as transaction costs, the risk tolerance of the investor, possible impact on the existing portfolio, and so on before making an economic or investment decision. We will now take a look at hypothesis tests concerning the mean of a population. And this has three sub-segments. Test concerning a single mean, and this is what we have already done in the previous section. The difference is that we will now take a look at the Z distribution, T distribution, and decide which one to use under what circumstances. We'll then talk about tests concerning differences between means and tests concerning mean differences. These two might sound fairly similar, but they have different meanings, as you will see in a short while. First, tests concerning a single mean. One of the decisions that we need to make is whether to do a Z test or a T test. This decision then drives the distribution that we use. For a Z test, we will use the Z distribution or the standard normal distribution. If we were to use a T test, then we have to use the T distribution, and there we need to make a decision on the number of degrees of freedom, which depends on the sample size, and that in turn impacts the critical values. So understanding which test to use is important. Here is a table that should look familiar because we used this exact same table in the previous reading. And the quick summary of what you see here is that if the variance is known, then you use the Z test. If the variance is not known, then you use the T test. So that is the high level summary, and then further details are fairly obvious in this table. Since we've gone over this before, I will not repeat. Consider this example. Fund Alpha has been in existence for 20 months and has achieved a mean monthly return of 2% with a sample standard deviation of 5%. The expected monthly return for a fund of this nature is 1.6%. Assuming monthly returns are normally distributed, are the actual results consistent with an underlying or population monthly mean of 1.6%? The way you set this up is as follows. Your null hypothesis is that mu is equal to 1.6 versus an alternate that mu is not equal to 1.6. And the reason we know this is the last statement, where what we are being told or what we are being asked here is, are the actual returns consistent with the underlying or population mean return of 1.6%? So that means that clearly 1.6 is the hypothesized value. We want to figure out whether the numbers we are seeing are statistically different from 1.6%, or in other words, is there a statistical significance associated with the difference between 2 and the hypothesized value of 1.6? Also, given that the null hypothesis must have the equal to sign, that would mean that we should have the equal to sign here with h naught, and the alternate is simply mu not equal to 1.6. The test statistic is x bar minus the hypothesized value divided by the standard error, which in our case is 2 minus 1.6 divided by sigma over root n. Sigma is given right here, the standard deviation of 5. Actually, this is not sigma now, this is the sample standard deviation, so denoted by S. So this would be 5 divided by the root of 20. Notice that we do not have the population standard deviation. We are using the sample standard deviation of 5%. That doesn't really change the test statistic formula, because we are simply using 5 from the sample as opposed to the standard deviation from the population. But the fact that we do not know the population standard deviation will impact the next item. In any case, we compute the test statistic, which is 0.35. Next, we have to come up with the critical values or rejection points given a 0.05 level of significance. Now, this is where we have to make a decision between a Z test or a T test. And notice, our population standard deviation is not known, so we use the sample standard deviation. That leads us towards the T distribution. If you recall from a table earlier, with a large sample size and a normal distribution, we could also use a Z table, but here our sample size is also small, it's less than 30, so we have to use the T distribution. We also need to determine the degrees of freedom, which is n-1 or 19, and you have learned how to use the T table from an earlier lecture. You need to do that now. Say this is your T distribution. We have degrees of freedom equal to 19, so that defines the specific T distribution. Level of significance is 0.05, and this is a two-tailed test, which means that we have 0.025 in each tail. The critical values or the rejection points from the T table will be plus 2.1 and minus 2.1. Make sure you look this up in a T table. Our test statistic 0.35 is falling in between. So the test statistic is in the region where we do not reject the null hypothesis. So the decision is that we do not reject the null hypothesis. Next, we'll talk about the rejection points for a Z test with alpha equal to 0.05. So there are three types of hypotheses we can have. One hypothesis is where the population mean is less than a hypothesized value, and just to take an example that we've discussed earlier, you can have a situation where mu is less than or equal to 2 versus the alternate hypothesis where mu is greater than 2. Now, in this situation where the alternate sign points to the right, that means that we are going to deal with the right tail. Here, the area in the right tail is 0.05, and if you look up your Z distribution, the critical value will be plus 1.65. The other situation is where mu is greater than or equal to mu naught for your null, and again, just to put numbers, we can say mu greater than or equal to 2 versus alternate where mu is less than 2. Here you will have to look at the left tail. The area over here is 0.05 and the critical value is minus 1.65. So this now is the rejection region, and to the right you fail to reject the null hypothesis. And finally, this is a two-tailed test where mu is equal to mu naught. Remember, whenever you have a plain equal to sign in the null, that means that you are working with a two-tailed test. So in this particular situation, still with a significance of 0.05, we have 0.05 that is now divided between the two tails. So in each tail we have 0.025, which means that the critical value will be a little larger. So in this particular case, if we have 0.025 in the right tail, the critical value for a Z distribution would be 1.96 and minus 1.96. And this highlights a point which many students are confused about, that given alpha equal to 0.05 or a significance level of 0.05, the critical value depends on whether you are using a one-tailed test or a two-tailed test. With the two-tailed test, you have a smaller area in each tail, and therefore the critical value is larger.